Okay, the following is a build-up as to why you can use certain forms of integration where a pattern emerges. If you look at the chapter for 7.4, it's actually you can actually do an integral for when you've got the differential of one function divided by the function itself. Now I'm going to devise that pattern using the polynomial. We're going to consider wanting to integrate the following equation or expression, which is 3x squared plus 2x all over x cubed plus x squared dx. Now, the traditional way to go about doing these, doing it longhand without the pattern, is to use express it in terms of partial fractions. So we need to rewrite this in terms of partial fractions. So that's our partial fractions. We consider what powers can I have on the top here. Let's factorise the denominator. So I've got 3x squared plus 2x all over x cubed plus x, which will factorise down to x squared and x plus 1. Now remember, when we're doing partial fractions, you need to consider if you've got a denominator x squared, the numerator for that could potentially still be a proper fraction if it has an x term in it. So we get an ax plus some constant on top, b, and then this one, value c. So there must be, if you've got an x squared on the bottom, unless you get another value where you've got an a over x, another factor of this, then you must actually leave it in that form. So generally, you solve using this pattern. Multiply through by the denominator. So you see that this is partial fractions from the earlier chapters. So we now get ax plus b multiplied by x plus 1. And on the other side we've got a plus c times x squared. Expand, we get ax squared plus ax plus bx plus c plus b plus cx squared. And we look at what can we solve for this. Well, I'm going to run this the other way around to normal. I'm going to look at the number terms. So we're equating coefficients. And so the number term, we have 0 on this side, and that must equal b. So we've got b term there which has an x, so let's try x terms. We have 2 in this one, and the only thing we have on the right hand side is a plus b. So that now means that we know a equals 2. And when we go to equating the x squared term, we've got 3 is a plus c. Tells me c must be equal to 1. So the integral has now turned into a separated out integral. And take that part and represent it in terms of ax, so that's 2x, divided by x squared plus c over x plus 1. And what we need to realise now is we're going to integrate each term separately. We take the black part. And we take that, and it's the integral of 2x over x squared, and of course they cancel, plus the integral of c was 1 over x plus 1, and that one I will need to do by using chain rule. So we're going to use another sub-use. This is where the pattern, why the pattern is useful. So I've now got q equals x plus 1, and du dx is equal to 1, which now means that I can replace dx, multiply up with du. That is a direct substitution on the land. So I can now do the integral of 1 over u with respect to u, we know is log u. And that means I've now integrated this term as well, because that one's a log as well. Let's go back to my black pen. So the integral here is going to be log, 2 log of x plus log of 1, or log of x plus 1, sorry, u is x plus 1, plus some constant. And I come through to, as I now need to look at this equation again. And the weird thing is, we're going to look at it and go the other way. We're going to complicate this and try and get all our logs into one place. And what we get is, we bring that inside, 2 times a log is the same as the log of value squared. And that is being added to the log of x plus 1. So we've actually used the power rule here. All the way around, and now we're going to use the product rule. If I do 2 logs added together, it's the same as the log of the product of them. So we've got x squared multiplied by x plus 1. And you might suddenly start going, hang on, I've seen them somewhere before. You have. When we multiply this out, we get log of x cubed plus x squared. And that was my denominator. Okay. So if I can actually find a function, it's possible to find it. There are multiples that allow you to sort this out in between. They talk about correcting for the value. But this actually leads to a pattern. So notice that's the denominator. We've now shown that when we integrate it, you get this log pattern. And what we need to realise is, what's the relationship between these two? Well, the relationship is the denominator function. If I differentiate it, x cubed plus x squared, we actually get the numerator. So what we were actually integrating was the differential of the denominator. What we were actually integrating here was the denominator is our function, the x cubed plus x squared, and the numerator was actually its differential. So it wasn't a completely random pattern that I chose. It wasn't a random polynomial. It was a specific pattern which allowed me to get this value. This is quite an important result. Because if you can spot that, if you can spot this relationship in integration, you don't have to do all the work that's happened above it. Sorry, I forgot to put in the black part on the other side. The integral of this is the log of the function of the denominator. Okay, so that's a demonstration of how this pattern comes about. It's a pattern that can be used if you can't solve all quotient problems like this, then you must match that pattern.